Good afternoon, everyone, and thank you for joining us today. I'm Wendy Heinzelman. I am the Dean of the Hajim School of Engineering and Applied Sciences, as well as a professor in the Departments of Electrical and Computer Engineering and Computer Science. And it is my absolute pleasure to be moderating this discussion today on fusion energy and the potential that fusion energy has for us moving forward. We have a wide range of registrants who are joining us today for this session, including alumni, parents, students, faculty, and staff. And this is going to be a wonderful discussion. So let's get started. Fusion energy is arguably the holy grail of energy production. It is a safe, clean, abundant, persistent source of energy and has the potential to completely transform the energy landscape as we know it today. So today you're going to hear about recent milestones in the field of fusion energy and the role that the University of Rochester's Laboratory for Laser Energetics has played in current and future developments in this space. Before I introduce today's speakers, I want to offer my deep appreciation to Bob Huang, who had the foresight to make today's program possible. Bob is a University of Rochester alumnus who made a significant investment in the University of Rochester in support of programming and technology and innovation in the Bay Area. And today, this presentation that we have is the third virtual event of the Huang Speaker Series in Technology and Innovation. So a huge thank you to Bob and his wife Lily for their support of the university. And now I'd like to introduce today's speakers. We're going to hear from two speakers, Radha Bahukatumbi and Chris Dini, both from the Laser Lab. Radha is a distinguished scientist at the University of Rochester's Laboratory for Laser Energetics. Her interests include the understanding of physics of inertial confinement fusion and identifying challenges in nuclear astrophysics that can be addressed using high-powered lasers. Radha leads a group called Women in Science and Engineering at LLE that has the goals of hiring, mentoring, and retaining women scientists and engineers. She received the Fusion Power Associates Leadership Award in 2021, and she is a fellow of the American Physical Society. Chris Dini is the director of the Laboratory for Laser Energetics. Chris is known as a scientific and innovation leader with direct experience running complex operations, especially in high energy density physics. He is a fellow of the American Physical, Electrical, and Electronic Engineers, the IEEE. At LLE, he developed strategies with an emphasis on bringing high-quality science and technology solutions to address key challenges in fusion, high-energy density physics, and laser technologies, while maintaining effective operations of academia's largest lasers and educating future generations of scientists and engineers. So with that, thank you all for joining us, and I will now turn it over to Chris, who will kick us off.
Good afternoon, everybody, and Wendy, thank you for the invitation to give this talk. So let me share my screen. Hopefully that will work. All right, excellent. So we're going to talk about inertial confinement fusion, which is the pathway to a cleaner and safer energy solution with fusion energy through one method, and we'll unpack that. So I will explain a little bit about LLE, introduce the work on fusion, and then Radha will do a deep dive and bring us back to the impacts, implications for energy. So the Laboratory for Laser Energetics, as Wendy indicated, hosts the two largest lasers in any university in the world. And I show you a view of the Omega 60 laser and the Omega Extended Performance laser, what we call Omega EP. If you get a chance to visit the lab, we'd love you to tour these facilities, but they are much bigger than what you would expect in a light lab at any other university that hosts a laser. And we do 2,100 shots a year for users across the country, for our own program, and for international participants as well. We typically have more than 100 unique users every year coming in to use these facilities. And we use them for three main goals sponsored by the National Nuclear Security Administration. One is innovation. These are large lasers, but they're still small enough for us to innovate and try new things. We do it for education. We're an academic institution, and we have typically something of the order of 60 PhD students in flight using these lasers or the derivative technologies at all times. Well, you can't educate and you can't innovate without leadership in science and technology. And the picture I showed there is Dustin Ferula, one of our division directors, getting the E.O. Lawrence Award, which is one of the highest scientific awards for a mid-career scientist issued by the Department of Energy. And our vision for the lab is always to be the leading academic institution advancing laser technologies, fusion, and high energy density science at scale. And I think we satisfy that vision now. And we'll talk through some of the things that we're doing that would prove that. And we'll also talk a little bit about the future as well. So innovation is in our blood. Since LLE was established in 1970, we have continued to innovate laser technology, primarily for fusion, but not just for fusion. And so this timeline shows some great examples. A big one being in 1985, Donna Strickland, who was a PhD student at the lab, working with Gerard Moreau, who was our professor, invented a whole new laser technique called chirped pulse amplification. I won't have time to unpack it, but that's opened up a whole new scientific arena, and it also ultimately led to the formation of bladeless LASIK. Donna and Gerard Moreau were awarded the 2018 Nobel Prize for that invention, and that happened at the LLE. And so, one of the things that we're looking at that we're mainly going to talk about fusion, is building the great grandfather of their invention, which would put the most powerful laser in the world here at LLE. And we're awaiting a decision from the National Science Foundation on that particular project. But all along, the innovation from how we smooth laser beams, how we control laser beams, has led to our ability to drive ICF, inertial confinement fusion capsules, far better than anybody else in a direct drive configuration. And we'll explain that later. But back to education. So innovation, education. We'll unpack as well the recent result of ignition at the Lawrence Livermore Labs. It was in the press. Pretty much every country in the world heard about it. It's a major step forward. That innovation train that I just showed you, many of the technologies that we innovated at the Laser Lab have shown up in the large laser at the National Ignition Facility that was used to get ignition. That laser is almost 70 times bigger than the laser we have here at Omega. So it's a massive laser, and it got ignition. It actually got more energy out of the target than was put in by the lasers. And here's a picture of the press conference on that result. And Annie Kritchner and Alex Zystra were the two PIs on the shot. One was a designer, one was experimentalist. They both did their PhD research on our the Omega facility at LLE. They were actually, unfortunately, not at U of R, but they did their work in our lasers. And so we're very proud of the fact that we actually are training the next generation of scientists who are going out making some of these major discoveries. But now to fusion. Why are we interested in fusion? Well, there's three main reasons. Fusion powers the Earth, whether it be solar cells, whether it be the nucleosynthesis of a supernova exploding and generating uranium somewhere in the universe that eventually migrated to Earth, whether it be driving winds through temperature gradients. The solar flux, and the sun is powered by fusion, basically heats the planet. The National Nuclear Security Administration is interested in it because fusion is a key part of the nuclear deterrent, and therefore fusion actually helps keep the peace. And finally, and what's causing a lot of excitement now, is fusion could be a local energy source. It's persistent, low carbon, good base load, and hopefully would have a lot more community acceptance in classical fission reactors. And so there's a lot of money getting put in there now by the Department of Energy, and Brad will explain that, for both magnetic fusion, which is exemplar I show here of the Commonwealth fusion system, or for inertial confinement fusion. So DOE is so driven by the need to make inertial confinement fusion work effectively that it actually sponsors three facilities. The lasers here at LLE, which are in the middle, that do the bulk of the shots for the entire ICF community in the US, 2,100 shots per year. That's more than about 80% of the shots. And we focus on direct drive fusion, and Rada will explain that. But we believe that's the most efficient way to drive fusion. The on the left, you see a view of the National Ignition Facility. It was a facility that was built at a cost of about $3.504 billion to be ignition capable. It was sized to get this country to be able, the first country to demonstrate ignition in the laboratory, and they succeeded. It was a 10-year journey once the laser was built, but the community got there in the end. That uses a different technique, indirect drive, which is less efficient, but obviously it worked. So that was a great success. And lastly, there's a third machine called Z that sits at Sandia National Labs, uses a whole different technology, very capable of doing engineering scaled samples for a lot of other experiments, but mainly it looks at magnetically driven ICF. So it's not like a tokamak that's magnetically confined. This is basically using magnetic fields to drive something really quickly, like we do with lasers. So it's such an important topic. Between those three facilities, you're looking at roughly $500 million of operational costs. So the US government in the shape of NNSA invests significantly in having these facilities. And the application for the laser facilities are threefold. One, laboratory astrophysics. We won't unpack that in this talk, but we could give you talks on quantum electrodynamic effects, generating fast electrons, protons, all sorts of interesting stuff, physics relevant to lab astrophysics. We can probe materials at extreme conditions. There's a Center for Material Atomic Pressures, funded by NSF, hosted here at University of Rochester, that came about because of the laser systems we have. But fusion is a grand challenge. You are literally bringing star power to Earth. We are trying to do something with a capsule that's about 1 millimeter in size compared to what the sun does. So it's a huge challenge, and Radha will be unpacking a little bit of that physics right now. Over to you, Radha.
Thank you, Chris. If I may share my screen. If you can stop your screen, I'll just share mine. Okay, so Chris mentioned the sun. He also mentioned that it was a long journey to get to where we are today. So I'll sort of deep dive into a little bit of that to explain why that is so. So nuclear fusion is the process by which stars produce energy. Let me share. So a fusion requires very high temperatures, approximately tens to hundreds of millions of degrees. And the recent experiment on the NIF was on more than 100 million degrees in the one implosion that they had. So this hot matter is very hard to confine, right? The sun does it because of gravity. And that's really the challenge that we face here on the Earth. How do you confine such a very hot plasma long enough that you can actually get energy, useful energy out of it, or enough neutrons or enough fusion reactions going? And that's really the challenge that we face. So Chris mentioned direct and indirect drive. So the way we do it with lasers, and I'll restrict myself to lasers for this talk, is using what's called direct drive or indirect drive. So on Omega, which is the laser that we have at LLE, the University of Rochester, we follow what's called direct drive, and that's shown here on the left. So you have a capsule on which directly incident are 60 nominally identical laser beams, and that results in conditions that you want for fusion, and I'll talk about that in a bit. The approach that's taken at the National Ignition Facility in Livermore, California, which received the big result that Chris mentioned. If you go on YouTube, you can look for this press conference and so on, uses an approach called indirect drive. So what that does is you have the similar type of capsule located inside this gold can called a hohlraum. And you have the laser beams which are incident on the walls of this gold can. They generate X-rays, and instead of the laser directly driving the capsule like we do at Omega at LLE, the X-rays then drive the capsule. Now there are pros and cons for each approach. The advantage of direct drive is that it couples nearly 4 times more of the laser energy onto the capsule than indirect drive does. So it's more energy efficient than indirect drive is. But on the other hand, indirect drive is less sensitive to the non-uniformity of each individual laser beam, that there's speckles on each of the laser beams. So there are pros and cons of each. And the facility, the National Ignition Facility, was built to study the physics and also to generate a large number of neutrons using the process called ignition and gain. Omega, on the other hand, does not have as much energy to do so, but it is a very, very valuable facility to study the physics. So the physics is primarily studied, and neutrons are produced using the fusion of what's called deuterium and tritium. These are heavier isotopes of hydrogen. Now, this is somewhat different from what happens in the sun. Sun uses different elements to do its fusion. But here on the Earth, we do this simply because deuterium and tritium have the highest probability of occurring in the conditions that we can achieve with these lasers today. So we use deuterium and tritium. So what happens is you have this neutron which is produced, and then it also produces this energetic alpha particle. Now, both of these are extremely key for demonstrating gain, but also if you want to head towards a nuclear power plant, having a large number of neutrons is also extremely important. So how does this process take place? So inertial confinement fusion, which is the process, not necessarily the process that produces energy, but it underlies the process that is needed for energy. It implodes capsules to develop conditions for what's called a hotspot. So the hotspot needs to be robust, and it results in propagating burn and resulting in high neutron yields. The high is in quotes here because the number of neutrons that you want and the number of fusion reactions that you want depends on the application that you have. So here's a schematic. So here's a target. Shown here is this layer of deuterium and tritium. You could have lasers or X-rays incident on it. And then the material ablates. And just because of Newton's third law, the rest of the shell implodes literally like a rocket. And the kinetic energy of the shell is then converted into very high temperatures in what's called the hotspot. And that results in fusion reactions that take place. So here you have a DT fusion reaction that takes place that produces a neutron and an alpha particle, which is basically a helium ion. So these alpha particles then go through the rest of the target, redepositing their energy, raising the temperature as a result, and which results in more fusion reactions that take place. So if you can persist with this process, what we would end up having is what's called a burn, which means that these alpha particles deposit their energy, more neutrons are produced, more fusion reactions take place, which in turn more alphas are produced, which in turn redeposits this energy, and so on. So this burn then can propagate through the target and resulting in a large number of fusion reactions. The conditions that are achieved typically in these types of reactions are really quite extreme. So here's an example from a calculation showing what sort of conditions are achieved. So you have a hotspot where you have very, very high temperatures, many tens to hundreds of millions of degrees, surrounded by a very cold shell of deuterium and tritium at extremely high densities, at around 1,000 grams per cc or so, which is, many, many thousand times what is the density of solid DT. And this occurs at very, very small length scale, so of the order of hundreds of microns. 100 micron is the thickness of human hair. So you start out with a pellet, which is roughly millimeter or few millimeter size, and then you ultimately compress it to very, very tiny, very hot, dense plasma surrounded by a cold shell. So if you have done it all right, you'll end up with gain, which is basically the amount of energy which is produced in the fusion reactions divided by the energy of the laser. So if you've done it right, you get gains greater than 1. Right? So we have gotten more energy out of this implosion than amount of energy that you put in through the laser. And so ignition and gain is really what we are after in the ICF program, or the inertial confinement fusion program. So there have been significant achievements on Omega and also the National Ignition Facility, which is probably what you've heard on the news of late. And that has set the stage for people trying to discuss what's happening with inertial confinement fusion. So here's an example of what the kind of results we've gotten on Omega. So we've started using physics-informed data science techniques, and they've led to significant improvements in fusion yields, or the number of neutrons that come out of Omega implosions. Now, as I mentioned, Omega really does not have enough energy for ignition or gain, but this is the place where we study what we need to do to improve performance. And many of the concepts that we have come across or we have identified in Omega implosions have direct applications to what we do on the NIF, what's being done on the NIF. In addition, Omega is also the place where you test out new diagnostics that are then implemented on the NIF and so on. So what's shown here is the amount of neutrons produced as a function of year. You see, we've made systematic progress as the years have gone by identifying the physics that we can tackle, improving technology, for example, cleaner targets, better laser delivery, and so on. So we really made significant progress, and some of it is directly applicable to what's happening on the NIF. On the right here, and this is the prediction that you would expect from a statistical model. If the model were right, your experimental result would be right on top of your, would lie along the line based on what you predict. And you see that we do a fairly decent job. And here's what would happen if we had access to a facility like the NIF, where you could have, a large amount of energy, like 2 megajoules, right? Which is about 70 times more than what we can do. You predict that you can, go into a regime where you can have burning plasma and so on. More recently, we've done much better than this, but this is really where we are. We have identified key areas where we can improve. So work on that will continue, and we'll continue to understand and also provide feedback to the NIF implosions. The result that made the shot that was heard around the world, as it were, is basically a series of shots actually that began in 2021 and culminated in a gain greater than 1.5. So we got 1.5 times more energy out of an implosion than the laser energy we put in. So all this work really began, it began, more than a decade ago. And since then, there have been systematic understanding in terms of how the laser interacts with the plasma material, how to get, better understanding of what the asymmetry or the non-uniformity of the implosion is, and better targets, cleaner targets, because if you have target has debris on it, it can compromise your target performance. So by systematically working on these both scientifically and also from the point of view of technology, there has been great improvements in the number of fusion energy that has been achieved as a function of time. And this, of course, culminated in the big shot, which is shown there, which is a gain of 1.5. So here we are, right? In the ICF world, we have great progress on Omega. We have identified key scientific concepts. NIF has demonstrated gain greater than 1. So where do we go from here? So of course, this work will continue, right? The National Nuclear Security Administration will fund this work to continue to understand the physics and get to higher gains for various national security purposes. But there's also the question of inertial fusion energy. So the key scientific concept that's needed for inertial fusion energy has now been demonstrated on the National Ignition Facility for the first time ever by humankind. So where do we go from here? And that's a big question that that we're all grappling with. So in 2013, the National Academy of Sciences said that basically, once you've achieved ignition and gain on the NIF, you have to now start thinking about a fusion energy program, inertial fusion energy program. And so as a result of which the Department of Energy has started thinking of those and so on. So, but why fusion energy, right? Fusion reactions have the greatest, highest energy density amongst all energy sources. So shown here is the same DT fusion reaction. So if you took the same amount of different types of energy producing sources. So for coal, I've compared coal with uranium, which is what is used in current nuclear power plants or deuterium-tritium fusion. You find that between coal and fission, which is what is used in nuclear power plants today, you get almost 3 million times more energy from a unit mass of coal. And fusion is even more efficient than fission is. You get 4 times more energy for a unit mass from fusion compared to fission. So energy density of fusion reactions cannot be beat in terms of any other source that we have. So that in itself is a great argument. But the other argument for fusion energy is that it can be clean, right? It's relatively pollution-free. It's carbon-free. It's on demand, meaning that wind and solar require the sun to be on and the wind to be on, but fusion is 24/7. And it doesn't require a large footprint, and there is no danger of a meltdown. So it can really be placed close to population centers. So I show all that here. And really, you want it to be placed close to population centers because by 2050, the prediction is that 70% of the global population will be urbanized. And so you don't want the hassle of having to deal with transmission lines and so on. So fusion has a large number of advantages: 24/7, environmentally acceptable, passively safe, abundant deuterium supply, and it's globally dispersed because you can get that from the oceans. And there are winnable proliferation concerns because the byproducts of this are not highly radioactive material that can be potentially used for national against nations and so on. So fusion has a huge advantage. We have demonstrated basically the underlying concept for it. But where do we go from there? So how would such a power plant work? And there are many pictures that people have come up with. There is obviously no operational fusion power plant yet, but it might work something like so. So here you have a target chamber. And from a target chamber, if you can somehow produce steam, which will then turn turbines and then which can go to electricity. Now, in current power plants, this target chamber, you can have, uranium rods if it's fission, or you can burn coal or natural gas, and then you can extract the heat, evaporate water, convert it to steam, and do it like so. But with fusion, it's somewhat different, right? So on the inside is where all the difference comes about. What you would do instead is take each of these pellets, send them into this target chamber, have, for example, some driver like a laser, which is imploding the target, and that would produce a large number of neutrons. And you use those neutrons to heat a lithium blanket, lithium, for example, and that then uses a heat exchanger to heat up water, and that would generate steam, and it would turn into electricity on the grid. So you would have to do this. You'd have to inject these deuterium-tritium pellets into this power plant here. You'd have to fire the laser, and then you would have to somehow extract that energy and send it out into the grid. So the challenges associated with this are, of course, the frequency with which you need to do this, right? We've demonstrated gain of 1.5 and a gain of 0.7 before, but you have to do this typically at the rate of 10 per second. People have all these estimates on what you need to do. And also deuterium is easily available, but there are challenges associated with having to breed tritium to fill these targets to send them back in again. So you need a driver like a laser that fires at the rate of 10 per second. You need to create these targets of good quality, inject them in, create these neutrons, which will then finally lead to electricity on the grid, and also create some tritium to do this. So there are many aspects that need development here, but the advantage of fusion is that it's very modular. So people can work on drivers and targets, whereas a different group can work on understanding what materials need to be surrounding this target chamber so that they can withstand the high flux of neutrons and X-rays and gamma rays that are coming out from these fusion reactions. So different groups can work on different aspects of a fusion power plant, but there are really a large number of aspects that need to be addressed. So what kind of gains do we need? As I said, we've demonstrated gains of 1.5 or so. So there are efficiencies at every step of power generation, and they require that eta D, which is the efficiency of the driver times the gain, should be about 10. And for reference, NIF took in about 400 megajoules of energy to produce about 2 megajoules of laser energy at the end. So its efficiency is less than 1%. So if you have an efficiency less than 1%, then you need a gain of about 100 or so. So we need to go from a gain of 1.5 to that of 100, which is very challenging. And you need to do this at 10 times per second. So what is under our control is really this aspect of it, right? The conversion of this into heat and electricity is very standardized, and that's not something we control. But what we can understand and we can make progress on is driver efficiencies and also improving target performance so that you can get better gain. Now, I mentioned that work will continue to increase gain by controlling various sources of non-uniformity, better physics modeling, how does the laser interact with the plasma, and so on and so forth. So this work will continue on both on Omega and the NIF to understand the physics. But there's also work which is taking place in terms of trying to understand how we can get better drivers, better efficiency in drivers. And Chris will briefly mention that at the end. But there are several other drivers that are being considered, solid state lasers, excimer lasers, heavy ions, which can give you efficiencies of the order of 10 or 20%, which then results in you wanting gains of about 10. So that is still, something within the realm of possibility. And as I mentioned earlier, there are many engineering challenges that need to be addressed for inertial fusion energy. So you have the wall of the chamber that has to survive for typical lifetime of a demo of a plant, which is about 30 years or so. So it has to survive all the X-rays and gamma rays that come in, and there are various mechanisms and various concepts that people are studying. Then somehow you need to get hold of tritium. Tritium is radioactive, but it has a very short half-life of about 12 years or so. So you really do not find it in nature. And so you have to somehow make the tritium. Right now, for all these experiments that take place, tritium is produced typically in fission power plants. But that's obviously not sustainable. But there are ways of using lithium and to have the neutrons interact with the lithium to produce tritium. And there's also the issue of having to recover the tritium after an implosion, because the IFE targets will typically burn 30% of the fuel. So you need to recover about the rest of the 70% or so. So tritium breeding, recovery, how do you use lithium to generate the tritium, and what's happening in the chamber, and so on and so forth. So that's another aspect that needs work. So clearly, we are not there yet in terms of a power plant, but we have demonstrated the basic concept in terms of fusion energy. So in addition to the technical aspects of it, there has been a lot of work in the policy landscape. So significant progress in policy legislation is already reducing the uncertainty in the fusion energy landscape and lowering barriers to entry by private entities. And that's very key here. So in the White House prioritized outlined 5 priorities in November of 2022 for reaching net zero by 2050, and fusion energy at scale was one of them. So clearly this is getting the attention of the policymakers. More recently, the White House held a decadal vision for commercial fusion energy, and it suggested that the DOE should start an agency-wide fusion initiative. And I will show you the next view graph on what's been happening there. And of course, regulatory uncertainty, right, is needed for anything that's relatively new, especially something like fusion. And the NRC recently regulated that fusion should be not be treated at the same level as fission. In fact, it should be treated like any other, low-level radioactive source, including isotopes for medical purposes. Therefore, they would fall under the same kind of category. So reducing regulatory uncertainty is also a big deal, and it allows for private players to enter the picture. So public-private partnerships will be very critical to explore the many paths towards fusion energy. Now, I spoke about 2 paths, really, direct and indirect drive. But within each of those concepts, there is a large number of variations in what you could do for the implosion. In addition, there's a concept called magnetic confinement fusion, which we did not cover in the interest of time, and which is really not LLE's work, which is also being explored globally. But fusion is going to be a huge enterprise. And it's going to be something that requires international cooperation and not just the role of the government. And so nearly 20 plus fusion companies have entered the picture. 6 of them are pursuing inertial fusion energy. And each company is pursuing a different approach. And to show you the interest in the private sector, this is the amount of money that's been going into fusion companies starting from 2012. And in blue is the government funding, it's also going up, but in green is the private funding that's going up. And this includes not just inertial confinement fusion, but also magnetic confinement fusion. So there's a lot of money, interest going into fusion, not only from the government, but also from the private sector. More recently, as part of this DOE-wide initiative, it announced a $46 million commercial fusion energy development for various companies. I would like to point out that Excimer Energy is a company that LLE has a partnership with. And we are exploring, they're seeking our help in trying to identify what the right kind of approach needs to be in terms of target designs and so on. So with that, I will hand it over back to Chris, and he can talk about LLE's recent work in drivers and what we're doing with trying to get to the high rep rates.
Yeah. Thanks, Radha. So as Radha pointed out, let me share my screen. So as Radha pointed out, the efficiency is a big win in a fusion reactor. And part of it is, as Radha mentioned, is rep rate, which we eventually want to get to, but I'll actually focus on a different topic. Because I mentioned earlier, Omega does 2,100 shots a year. A fusion reactor would do 2,100 shots in 3.5 minutes. So getting to a rep rated laser is going to be key with high efficiency. And we believe there are techniques out there with diode pumping, etc., actively cooled amplifiers that would allow us to get that. Because right now our shot rate is limited by how long it takes the laser to cool down because of that inherent inefficiency. You put a lot of waste heat into the laser and you have to let it cool down and be ready to operate again. But what we see is the key breakthrough that's required are lasers that can very, very efficiently drive the fusion process in direct drive. And Radha did a great job explaining that. And it's going to challenge your understanding of lasers. It's challenged my understanding of lasers, because when you did an optics course or lasers were introduced to you, you were told, what are the 2 key interesting things about lasers? They're very, very directional, and they're very, very monochromatic, either like a color. Well, it turns out, and we won't unpack all the physics, but many of our scientists in our computational groups or experimental groups have evolved an understanding that sort of led to a challenge to our laser technology groups, and they've risen to the challenge to say, well, we like the directionality of lasers, we like the control of lasers, we like to keep them very smooth, But the one thing we need them to be is not monochromatic. We need them to have some spectral width, to have some color. And right now, we're in the final stages of construction of a laser we call Flux, the 4th generation laser for ultra broadband experiments. The picture up in the top right-hand corner shows where it will sit relative to our 2 other big lasers just now. But the goal is to be able to bring in a laser beam that is actually got 1.5% bandwidth, i.e. the width of the laser in the frequency space is 1.5% of the wavelength of the laser, the line center of the laser. That will solve a multitude of plasma problems that I won't bore you with just now, and should allow us to create a very efficient drive laser independent of scale. Because unfortunately, Radha mentioned, what if we had a 2 megajoule laser? Well, if we don't solve some detailed plasma physics, even if we had a 2 megajoule laser, we would not get the efficient performance that we want. So this Flux laser is the next big step in showing that we can actually generate a laser that allows us to conquer a number of sort of plasma issues that have haunted the community for a few decades. And that will open up the technical path to a very efficient laser for fusion energy in the future. So stay tuned. The laser is under construction. We've punched holes in walls for the beam tubes. The back end of the laser is actually up and running, the pump for the advanced laser technology. And we're put all together, and the goal is starting in 2024, we should be doing experiments and start understanding was our theoretical predictions correct. So I'll close with one slide that actually talks a little bit, not about our normal targets, but just shows you a demonstration of our innovation and capability. As Radha mentioned, besides making sure the laser is ultra precise, having ultra precise targets that are manufacturable on a fast time frame will be important. So we're looking at 3D printing, but on a small scale, using 2-photon polymerized printing that have allowed us to design some very, very advanced targets. Now, I could show you those targets and you would look at them and go, those are nice. Is it a picture of COVID? It's, they're hard to tell just how precise this is. So our target fabrication group did this as a demonstration for Representative Morelli when he came, our congressman, when he came to visit. All of you who are alums or parents of students or incoming students should recognize the Russell Rees Library. That is made here in our lab using 3D printing, and the space bar up there shows 20 microns. So that is a 3D model at 1 millionth linear scale that would fit on a human hair. You can see all the features there. That's how precise this manufacturing technique is. And we believe that will actually open up another path to advanced targets as well. But due to time, we can't go through that whole story as well, because that would take another 40 minutes. So I will close with, hopefully we've convinced you that LLE really lives up to the term Meteora. Ever better. Every year we train better students, we innovate, we train more students, we advance the field of ICF and hopefully open up the gateway to inertial fusion energy. And so with that, we'll open up for questions. Thank you.
Great, thank you, Chris and Radha. That was really an excellent overview of not only the history and where we are with fusion energy, but where we're going in the future. So we've had a lot of questions coming in on the chat. I'm going to try and get to as many as we can. A number that have come up have been about safety concerns. So I'm wondering if Radha and Chris, either of you could talk about, are there any safety concerns? Is there any radioactive waste that is created? Are there any other sorts of safety concerns that fusion energy will create that we should be working on, worried about, that sort of thing?
Yeah, maybe I'll take that one, Radha.
Okay.
So, one of the large concerns, well, I'll start with climate change, right? So any fuel source that is, generating large amounts of, carbon and carbon dioxide in the atmosphere potentially has a safety impact. It'll take a long time. It'll be on a large scale. We don't know. People worry about fission reactors, especially if they've watched the HBO show on Chernobyl, because it has a lot of radioactive material centrally located, and that includes what's called transuranics, things like plutonium. that have very, very long half-lives. I could go into a whole policy talk about what we could do in fission space, but the bottom line is that's one of the things that has caused a lack of social acceptance on fission reactors. Fusion, Rada did a great job of pointing out how you use those neutrons to heat the blanket and to create the tritium to refuel the reactor, but those neutrons also activate a lot of the material round about it. But that's really sort of low-level radioactive waste. It's the sort of stuff that basically you can deposit into many, many commercial sort of waste sites. And it doesn't create this sort of very long-lived isotopes where you have to figure out how am I going to manage this for 10,000 years. So you can't say there's no safety issues, but they're much minimized, almost on the same level of concern you would have at a medical radiation facility and stuff like that. Maybe at a slightly larger scale. So, if
I can add one more piece to that. Yeah. So one of the challenges, of course, with fission is the fear of meltdown, and we've seen that in 3 Mile Island, Chernobyl, Fukushima, the most recent one in Japan, which was a perfect storm, right, of an earthquake, and which ultimately resulted in the meltdown. Fusion doesn't have that problem, because if you've done something wrong, the whole thing just fizzles. And you just don't get any power out of that power plant. So there is no fear of a meltdown at all when it comes to fusion. And that makes it much more safer inherently than fission.
Okay, great. Thank you. Another question that has come up a couple of times in different ways is, what is your estimation of timeline? When are we talking a decade, 100 years? When might we actually see commercially viable power coming from fusion?
I'll let Rada take that one first.
That's very convenient of you, Chris. So if we could predict the future, we wouldn't be here with a very carbon-intensive fuel source, obviously, right? So a lot depends on, as I mentioned, there are scientific challenges, there are technological challenges, and then there are challenges of scaling it up to a demo plant, and then a power plant that is fully functional and connected to the grid. So there are really scales of challenges here, and a lot depends on the rate of progress, right? So a lot depends on how do we understand the science and get to gains which are of the order of 100. How do we design rep-rated drivers and targets that are of high quality? How do we breed tritium? So all these are really just starting off. And a lot depends on what the funding scenario is, for example, what resources are put into it, and so on. So right now, it looks promising in the sense that the government is committing some amount of money to it. The private sector is very interested in fusion reactions for all the obvious reasons that I stated. But really, getting to a fusion power plant that's connected to a grid is, I would say, the scale of a Manhattan-type project, really. It is a large-scale project which requires people with different skill sets and different technology developments had to happen and so on. So it really depends on the trajectory as to what would happen. But I would be very happy to see it happen, the next 4 or 5 decades. There are private industry. There are a couple of companies. One of them, Helion, was in the news recently. It's promised to deliver energy to Microsoft by the end of the decade, which is interesting. But private companies obviously are more ambitious, but we understand the challenges.
I can build on what Rada said. I mean, and she'd mentioned it in the talk, the Department of Energy, Secretary of Energy Granholm has laid out a decadal vision, right? So, can the Department of Energy drive something that's more meaningful in the next decade or so? So, and the excitement really is twofold. We didn't really talk about the magnetic fusion, but the ignition demonstration that we mentioned really shows that you can have gain. You can actually get a situation where you get more energy out than you put in. A lot of other efficiency things to work, but that's now been shown. The other thing is the magnetic systems have better duty cycle, right? They're already demonstrating fairly long-lived plasmas. They haven't shown gain, but they're actually starting to show, well, we can hold a plasma and generate output power, not exceeding a gain of 1, but for tens and tens of seconds. So on both of the technical paths, there have been such significant achievements, and I think that's what's driving the future. But since this is Wendy's sponsoring or moderating this one, I have to sort of reach out and, basically say this is a great time to be in engineering, because just in this field alone, these are big science challenges, amazing material science, material engineering, operational systems, just huge sort of interesting challenges for the world, and and hopefully for our US sort of industry as well. So definitely an exciting time, and I'm glad to see, as Radha said, that the Department of Energy in particular is really starting to put a focus on moving it just from the science world into an actual engineering scale demonstrations.
Right. Well, and it was interesting. You mentioned all of the different fields, from material science to the mechanics to the physics. A lot of different areas are needed. A question came in: what about AI? So now AI is sort of transforming how we look at experiments in the physical sciences to operations and how we run operations. Have you thought at all about, or what can you tell us about the impact that AI is having, or that you see or you think AI will have moving forward in this space of inertial confinement fusion?
Well, great question. I'll start, and then sort of Radha will definitely add a lot more detail. So I'll use ITER as an example, which is a large magnetic tokamak that's been built in France, which is a multinational project on fusion. That has a vast array of control points. And so already in the smaller tokamaks, people have been showing how they can use that sort of continuous operations to feed some machine learning type networks to evolve control systems beyond just scripting. So now, the system can sort of digest a lot of information and learn how to control the reactor to keep it stable. In ICF, Radha mentioned it, we've used a very simple form of machine learning, a statistical model, but we actually have people right now working on how we use 2D simulations to better train a model that we could then have guide and learn from our experiments. In fact, there'll be a press release probably soon, next few weeks, on the fact that we've just re-entered the top 500 supercomputer list. We're like 300 and something, but we've just bought a 2.6 petaflop computer system purely to drive more calculations, because then we can do more 2D calculations, which are more consume more time to potentially train AI systems to then sort of ingest the experimental results as well. So I know, Radha, if you wanted to add something to that.
Yeah, so AI is going to be really very big in this business, and I sort of see 5 areas where that can happen. The first one is science, right? As I mentioned, we really need to understand how materials under these really high densities and temperatures behave. So AI is already, ML and AI, machine learning and AI has already entered that. And there are a number of groups, including one at LLE, which are looking into better predictions of properties of these materials so that we can understand what it takes to drive these kinds of materials into the conditions that we need. So that's the science. As far as fusion energy is concerned, there is the whole rep-rated aspect of it. So there is control, right? So if you have to fire a laser 10 times a second, you need to have really good control over the laser. And so AI can help a lot in determining what the next shot needs to be based on what has happened in the previous shot. So this rapid turnaround from one shot to the other at the rate of 10 per second, AI can play a big role in that. AI also plays a big role in diagnostics. How do you interpret what you measure? Or how do you do edge computing, right? So if you are shooting the laser at 10 per second, you need to know what has happened before you can shoot the next one so that you can accordingly adjust. So can you use edge computing, which is computing at the source where the data is generated? So that's another aspect where AI/ML can play a role. AI/ML plays a big role in code development, and this is a new area that's actually coming up. The physics of this implosions is very, very complicated, and it spans a whole range, not only of densities and temperatures, but also conditions where the plasma behaves like a fluid, sometimes it does not, and to model all this accurately is very challenging. So AI codes that sort of bridge the gap between the two are also becoming of more interest, and people are starting to talk about these types of ideas. And finally, there's a target design. what do you shoot and what should the laser history profile look like? Just to design these types of targets also requires the use of ML and AI. In fact, there are some graduate students here who are working on those types of things. So I sort of see AI ML as broadly, influencing the entire, not only ICF approach, but also IFE.
Great, thank you. And you mentioned, educating students. And so I'm curious your thoughts on what is the workforce going to look like? Do we need to scale up the number of students trained? And what are the types of backgrounds that you would think that maybe some potential students or incoming students who might be on the call, or people who know students who know kids who are looking to go into this area, where do you suggest that they focus their studies? And what are you thinking in terms of workforce development and what LLE can do moving forward to help with that?
Radha, do you want to go first?
Okay, so it's all the areas that I mentioned, right? So basically we need students who are interested in pure science, who are interested in applying novel computational techniques or developing novel computational techniques, combining AI with GPUs, using of GPUs or using of exascale machines, which requires a completely different computing paradigm. So we want students who are interested in the science, we want computer scientists, and that sort of pushes forward the theoretical scientific aspects of it. We want engineers who are innovative, who are interested in developing new technologies, because we need high rep rates, we need better efficiencies, things like that. So optical engineers, control systems, electrical engineers, you name it, we need those types of engineers. We need people who are very well-versed in doing experiments or who are willing to learn to become well-versed in doing experiments, identifying novel ways of diagnosing what's going on in these types of experiments so that it can feed back into better predictions, which would feed back to better, path forward, a more direct path forward to higher gain and so on. So we want experimentalists. So really it's a range of, it's so highly, multi-skilled that we really need a range of people with different skills really in this field.
Yeah, no, thanks, Radha. And there's a few things that we're doing at LLE. One, we are expanding the number of our graduate students that, they come from Wendy's group or physics and astronomy, basically from ASC, different departments, but, they do their PhDs here. And, we've now passed 60 PhD students working here. We also hired an academic coordinator, Laura Cappy, who's doing a great job in tying together our undergraduate activities. And so I think this year we've had the most undergraduates come in for the summer that we've ever had, because again, we need people, the NNSA needs people, and the fusion industry really needs people. In fact, Radha mentioned the YouTube on the press conference on Ignition, and right at the end, Marv Adams, former professor of Texas A&M, who's now running a big part of DOE, said, and by the way, we're hiring, and so I said like 3 million, 3 or 4 million views. And so it's basically, there's a huge demand. But back to one of the things that LLE does, and Radha just touched on it. If you come in any of those areas that Radha mentioned, the thing is you are working with people in all the other areas that Radha mentioned. You will work with, great technicians, theorists, engineers. And so when you finish at LLE, you can go to a national lab, you can go to a fusion industry, you can go to a defense industry, you can go to, cutting edge biomedical, and you will have seen how to do that multidisciplinary large scale science that just gives you a rocket launch into the rest of your career. So yes, we're hiring people and students. So.
Great. And sort of related to that, a question came in about what is the environment for women in this field at the national labs and at places like LLE?
Radha?
Okay, I guess I have to take that one. So actually, the number of women in this field generally tends to be, the fraction of women generally tends to be low. And that's typically the case in the sciences, right, which are not the so-called soft sciences. The hard sciences, whether it's physics or engineering, typically have, on the lower side of representation of women and other gender minorities than the biological sciences do, for example. But having said that, there is a lot of impetus towards trying to not only hire, but also retain women at LLE and also at the national labs. And we have groups within LLE that perform, that work as allies, that speak up for other women and other gender minorities. So diversity is becoming a focus at LLE and also at the national labs, and typically in this field also. And we have seen the number of percentage of women in this field rise from about 6% about a decade ago to more than 12% now. So there are concerted efforts to try and hire and recruit and retain women and support them in the work that they do.
And Radha, if I can add into what Radha said, I mean, Radha herself personally, is deeply involved in, our Women in Science and Engineering group, and actually gave an incredibly good seminar to the whole lab about, what we have to understand, with that sort of demographic imbalance, about how we change to actually fix that. Also, I would say the glass ceiling is starting to crack a little bit. For a long time, some of the national labs would have, a deputy lab director that was female, and then Sandia Jill Ruby became the first lab director in the history of the labs, which basically started in the Manhattan Project in the 40s, became the first female lab director. She then left and is now the head of NNSA. And so that was, great progress twice in her career. And then Kim Badil became the first lab director at Livermore National Labs. So, it's a long journey. It should be much faster. But, with people like Radha giving sort of us good advice, and, the commitment of the University of Rochester and LLE and the whole of the plasma physics community to address this, we will make progress.
Great, thank you. Well, I think that is a great way to wrap this up. I'm sorry we didn't get to all the questions. There were a number of good questions that came in the Q&A chat window. We will be sending out a recording of the program to those who attended in the next week or so. So if you missed anything or want to see the slides again, you'll have access to that. But I really want to thank Chris and Radha. That was a wonderful overview. I learned a lot. I hope everyone in our audience learned a lot. I've seen a lot of comments in the Q&A field. People really appreciated learning and understanding about this important area. So really appreciate your time. And thank you to everyone who joined us today. We hope you have a great afternoon and hope to see you all at a University of Rochester event soon. Take care.
Yeah.
Thank you very much. Yes,
Take
thank
care.
you, Wendy. This was a pleasure.